All right, so good morning. This is session 10 of the distribution short course. Session 10 is all about distribution system kind of operations. So, what are we doing with these operations on a day-to-day basis or a month-to-month basis or a year-to-year basis? So starting to figure out what, everyone wants to think like, oh, well, all the pipes in the ground, there's nothing to do out there in distribution. It just does its thing. That's far from true. I think any of you that work in the industry know that to be the case. There's lots of things you can do in distribution. Distribution can be a complete time suck. There can be so much work to do that you honestly struggle to do anything else. It just kind of depends on maybe the age of your system, the upkeep and maintenance that's been performed, and everything else. So it can take a lot of crew. If you're a very active system that does a lot of preemptive maintenance, you can be very busy in distribution. But I will say that the nice part about that is that you can schedule that time versus people who are not kind of in the mode of doing preemptive maintenance. They tend to be doing reactive maintenance. So in other words, water main breaks and things like that occur, they're chasing them all the time and maybe trying to get stuck valves or hydrants or other things that aren't working properly fixed when they've had to use them for whatever reason. So we're going to just talk through a whole bunch of pieces around operations today and just make sure we have a general understanding. So kind of starting out here. So operations, what did you do today, right? What was the thing that came up today? Well, in this person's instance, it was a bad day. If somebody hit a building, a well house or a treatment plant that was associated, could have been a pumping station in this example, and caused a lot of problems, right? So right out the gate, woke up thinking they were going to do one thing and they're doing something else. And the scary part about it is that this happens more often than you would think. We actually just in the last few months had a car that had hit a well house in the southwest part of Michigan that has caused some significant issues. It knocked the building off its foundation. It destroyed all the controls for the wells. There was a lot of other things that occurred there. So, you never know what you might come into work and have to do that day in our business. So routine or emergency work. This is where things can get a little bit interesting. If you are having to go out and get into an emergency style status, that's a lot more difficult than when you're out there trying to get your routine stuff done. Things can change very quickly depending on what's happening. You can go from a nice dry area that you're working in to something that looks more like this. This is the immediate result of digging on a 12-inch main that got hit. So you just didn't know that there had to be a tree or something in the way that caused a massive problem to the rest of your day, right? So routine operations can be anything but boring, but there are sometimes boring aspects of it, right? Having to check on meters, having to do simple hydrant maintenance, doing water main checks in certain areas to see how flowing and cleaning is going along, doing valve turning programs, or just literally doing rounds around the systems to just check to see that you don't have a fence down, you don't have a vehicle smashed into a building, you don't have a door that's been busted into on a pump station or something along those lines. Just making sure that you've had a routine visit to all the locations within the distribution. What you'll find though is that in an emergency, you get a chance to be a hero, right? You can go out, you can fix a leak, unfreeze that frozen thing, work on those flooding areas, try to get to the low pressure points of the system that are causing customer complaints and everything else. But at the end of the day, I would say it's a bit of a thankless hero. People don't necessarily call up and say, hey, thanks so much for getting all that done. They're calling more saying, hey, why is my water brown running into my tub? Or how come I have no water? What's going on? And just complaining about the lack of ability to access the water that they are a customer for. And it makes sense. We understand it. You praise people when you see it, but a lot of times in our regard, nobody sees exactly what we're doing. So I would call you guys unsung heroes. All right, so a couple of things to understand. You've got a few phases here. You need to make water or purchase water or get access to water in such a way that you can distribute it. Then once you've distributed it, which is phase 2 there, phase 3 is that you collect revenue from it. You know, we don't like to think of the water industry as a business, but it is. It is just that. It is a business. It may be in sometimes a not-for-profit. It's showing profit here, but a lot of times our municipal systems, we're kind of in a not-for-profit or net neutral, not net gain, right? If we're doing a net gain, it's only in the sense that we're trying to put money aside to be able to do upgrades or maintenance to the system in kind. So it's really not a net gain overall, right? If we're able to put some money into the water fund, it's really so that we can replace water main and other things that we have to do in the future, not necessarily making a profit. So, you know, it's a difficult balance to make sure that we are always correctly doing this, especially since a lot of times in municipalities, water rates are kind of set by the elected officials. And in those situations, the elected officials don't always have flavor for increasing rates and irritating their constituents. So there's things outside of our control, but the things that are within our control, we need to focus on, right? Making sure our meters are working properly, making sure we're getting out there and getting our meter readings done appropriately. All these things can help. And then having good policies on what's going on. So essentially what this slide is trying to say is, so what all comes into the phase two, right? It's simple to say we aggregate or we purchase or we do whatever we need to do to have drinking water. We disperse it. That's all of phase two and all the work that goes into phase two. And then phase three is this simple bill collection, right? So when we're talking about that simple bill collection, we need to, though, make sure that our billing is accurate, it's reliable, it's fair, and it's transparent. People understand why our fees are set to where they are and what that means and what's going on, and that we're getting appropriately paid. If we're not retaining the revenue that we're supposed to, then we need to do something about that, because you can't run a water system for free. It just doesn't happen. While having access to good, clean drinking water, you know, people want to say is a right, and I don't necessarily disagree that that's a right or a privilege that all Americans should have. It doesn't come free. You know, it does still come with need. So it doesn't, you know, if you want free access to water, it's available. You can go to any one of the Great Lakes, rivers, ponds, mud puddles that are around here, and you can have free water all day long. But if you want that water to meet regulation and be clean and appropriate for you to consume, then that takes a little work, and that work costs money, unfortunately. So, or fortunately, however you want to say it, at least in our business, it's fortunate, right? Because then we make money at the end of the day for ourselves and our families. But essentially, those services have to cost. Water meter installation. This is just showing a way that a water meter can be installed. This is a meter horn. So it looks like a loop. It's not really a loop. The water comes in from the road here through the service line. It then comes up and it ends up having a preferential path that goes through. So these two lines are disconnected from each other. They're not all in the same. There's appropriate shutoff valves to isolate the meter so that you can change the meter out or work on the meter appropriately in this scenario. And then we have installations like this. So the first issue that I see here is that there's no isolation valves around this meter. So if you needed to be able to work on this meter, you'd have to shut the entire service off on both sides. You'd have to figure out how to shut things down on the homeowner side, and you'd have to shut down the curb stop on the municipality side or the city side. The other thing that I see that's a problem here is talk about having dissimilar metals connected, right? You've got galvanized, you've got brass, you've got copper, you've got all kinds of things associated here, not to mention a whole bunch of electrical grounding is what it looks like, which can also be an issue, right? Even though it's code a lot of times to ground to the water lines, it doesn't always do the best things for our water lines. And Matt will talk about that later today when he starts talking about corrosion control and corrosion in general. All right, so here's a meter pit setup. Sometimes people get a little shook up by these, but essentially, it's been a while since I looked at this picture. If I'm orienting myself right, I would say that the service is coming up here from the water supply, coming through, going around this bend, going through the meter, coming into this area, coming up here, and then going out to service. I think it's in that path because, one, the way the meter set is, I believe that it's flowing that way, but then also because this right here, I think this is probably an installation for an irrigation system. I believe that this is probably an air chuck blow off for an irrigation system. That's what it looks like to me, but I might be mistaken. I didn't take this picture, but that's what it looks like. Quickly, but yeah, so this is not an interconnect. This is just a brace between the two horns. This is just a meter setup that gives it structure, right? So this is just brass holding these two pipes. These pipes are in a U shape that bend around, go through the meter, bend back up, and go out to service. So meter readings, there's lots of different ways that meter readings can be done. We've got literally go read the meter and write the numbers down from month to month. That's one way to do it. Luckily, we're getting very far away from that in many regards. But even though you don't have to necessarily enter a home anymore and read a meter specifically, or we haven't had to for quite some time for most areas, they're still time consuming. If you've got to go to every location within your distribution system to pull a reading, whether that's through a radio read or through visual reading or whatever, that takes time. It takes time to go to each location. So there's ways of speeding that up. But then I guess the other thing to note here that they're showing is that it can be hazardous. I mean, I know none of us are out there rolling around in segways. I'm not even sure where Ernie put that picture in this slide. Ernie Sarcopato, if you remember him, he's no longer with Eagle, but was with Eagle for quite some time. I'm not sure where he pulled that picture from, but essentially the idea here is that you'd have to go from home to home and read the radio reads to get at least within signal distance, if not sometimes right up to the census signal creation and almost tap the dang thing. But either way, as you're out there and about and you're heading on and off from private property or moving around private property, you've got dogs, you've got crazy people, you've got all kinds of things, cars, just vehicle traffic in general that can all be of a concern and hazardous to you. So you have to keep your senses about you. The main thing that I would say, meter readers and those that are out in the system getting readings, if you're driving around in a truck or if you're actually walking across property, is that you're really kind of the eyes and ears of the distribution system. You're the one that's out there day to day or week to week, depending on how often you guys do readings, understanding what is going on in the distribution system. You're the one that as you get closer to a home, you can look and see if there's lights on, if there seems to be activity there, or if it's a vacant house. If it's a vacant house and you're doing walking through property, you can maybe look at meters, listen for water leaks, look for daylighted water. You can do all kinds of stuff while you're there. You can be present. And being present is an active part of proper operation of a distribution system, right? If you're paying attention to what's going on, then you're going to be more quickly to identify leaks, misuse, and other issues. If you are going to a house that's clearly occupied and every month you're getting very low to no readings off a meter, then that has to start becoming suspect. You might end up finding out that that individual that lives in that property has put a blank in between your meters so that they can get free water, and then occasionally throwing it back in to get a few readings so that it's not a suspect. There's things that happen out there, or the contrary could be true. You could be noticing, this looks like a vacant house, doesn't look like anybody's here, but there's thousands of gallons of water being used every month. That could mean that there's a leak in that facility or there's something else going on. So it's good to be aware and present. You're also a lot of times going to be the face of the water system. As you're moving around through all these properties and gaining readings, people see you. They see you out there. You might get stopped. They might talk to you. So, make sure that these folks are ready for those things. They understand those things, and they know how to put the best foot forward for the water system. All right, so this is a little bit of what we were talking about how we can get away from walking. So there's drive-by MRs and there's fixed base AMI systems out there. So your fixed base systems actually kind of work more on like a line with like cell phone type signals, how it can come back to an intermediate tower, and intermediate tower can talk to a larger device, and then it can all be downloaded to a central location so that nobody actually even has to move throughout the distribution system to take readings at all. They get it instantaneous. These are very interesting systems because they can actually record and log on a minute to minute, hour to hour, day to day, depending on what you set it up as. And it can identify when there is excessive or abnormal usage at a location. In a sense, being able to tell somebody, hey, I think You might have a fixture that's leaking in your home, or you might have a broken pipe because we're really seeing a lot of flow. Something seems to be going on, and you can actually tell them, hey, check on your home plumbing. Those are important pieces. The drive-bys are awesome as well. They just don't give you as much real-time data, but you can actually have from a truck in the road, driving at a fairly reasonable pace, you can just pick up the radio reads and it'll download everything to a logger, and you can get it onto your system and then back up to the central system and have all your billing and everything go that way. So there's several technological increases that have occurred in the last, I'd say 20 years. It's pretty cool stuff. This is kind of an older setup, but still very interesting. So a lot of times municipalities used to have the ability to break down meters, repair them, install new parts within the meter, and then reinstall meters out there. So this was a really good setup that one of our communities out there has, where they've been able to test and do change outs and everything else to meters to make sure that they're proper and accurately reading flows and other things. So it's pretty cool, but it's becoming a little less and less. We're getting to the point now where meters seem to be a little bit more in the replace mode and not the repair mode. Hydrants. Hydrants are one of the most important access points to a distribution system. Yes, they are out there with a thought or the primary function of fighting fires, but it gives us access to an underground system that we can otherwise not really tap or do anything with. So hydrants become a very important part of distribution maintenance and operation. In this scenario here, this was a system that got called out because their firefighting folk were using the hydrant, and after they were done using the hydrant, they closed it off. The municipality was very quick to blame the firefighting team for breaking the hydrant, is what they thought, because they couldn't get the hydrant to turn off. As much as they would crank and try to do stuff, it just would not turn off. Through further inspection, they started seeing like, oh, there's actually something stuck in the valve stem that's forcing the valve to not be able to seal. And after they got that removed, they found out it was a stray gasket from water main installation. That's where that extra gasket went. So, you have to understand your operations of these hydrants. I'm pretty sure you had a moment with components where they talked about how hydrants are. I'll back up just a minute to just refresh you. If you look at this, the hydrants close against pressure. So as long as you don't have an obstruction like this, you should be able to mainly and mostly close down a hydrant. Even if the seal on the valve itself is bad, you should be able to get a very good reduction in flow. It might not turn it off entirely, but you should be able to close it down and get something that kind of seals. So in this scenario where it was clear they were not able to get flow to close, you have to know something is up, because the pressure of the water system is pushing against the valve head, which means that it would want to close more than anything. And as traffic breakaways are, the same thing with these stems. If these stems or some portion of the stem was to break for some reason, this valve itself would want to force against the seal point and close off. So in this scenario, they should have known there was an obstruction of some sort. So that obstruction could have likely been removed and identified well ahead of time had this hydrant been normally and routinely maintained and the water main flushed often. Maybe not, maybe it was stuck in such a way that it just so happened to finally break free and come into that scenario during that fire session or that firefighting session. But more than likely, it just had not been fully flushed for a long enough period of time to allow that gasket to find its way in there. Hydrant maintenance activities. Flowing hydrants periodically is an extremely important part of maintenance in a distribution system. Making sure that hydrants are operable is very important. Identifying leaks from the valve seat and the O-rings can be important. We want to make sure, because over time they can get deformed, brittled, and other things can happen like we saw here. So making sure that you understand when the hydrant has a leak is very important, especially when we get into Our climate, where we have winter operations, if you have plugged weep holes on those hydrants and your barrels fill over the winter, you can get them froze up solid and cause all kinds of problems. So we want to know when there's leaks. The only way to know when there's leaks is to get out there and open and close a hydrant and make sure you can see that the flowing conditions have stopped. So caps, the cap should be cleaned, greased, and in good condition on all your hydrants so that they operate as intended and they're not stuck shut. Your operating stems are the same condition. They should be greased and easy to operate. The nut should be in good condition. Shouldn't be a rounded blobbed mess from people putting all kinds of pipe wrenches and stuff on it. Hopefully you have the appropriate stem wrench so that you're doing those correct. All vegetation and soil should be at least 12 inches below the nozzle bottom so that you can keep good clearance and good visibility of the hydrant. Paint is a condition that should always be noted and paid attention to make sure that they remain visible and remain in good condition so you don't get rusting and other issues occurring. And that the isolation valve is actually exercised so that if you do end up having an issue with the hydrant, you can take it out of service without having to take down a portion of your water main. As you can see here, this is a not well-maintained hydrant. So you can see the paint is in complete disarray. There's been years and years and years of growth from vegetation around this hydrant. So this is an example of a completely unmaintained hydrant and not a good situation. This is also another hydrant that has obviously not been properly maintained over time. And this one is even a worse scenario because this specific one is actually a drain down hydrant for the stand tank that's behind it, or the elevated tank that's behind it. So, we have to make sure that we maintain these things so that when they're needed to be used, it's appropriate that we can use them. In this situation, this is just clearly an inactive hydrant. This is one that should just be removed from service. We should be trying to take a little bit of pride in our water system and not allowing things to get to this point. And if we're not going to have a hydrant that is serviceable or usable, we should be removing it, making sure that we have a proper cap and a proper backstop to that cap on the line and getting it out, or just replacing it altogether with a new one if there should be one there. We should not get to these situations. If you have a situation like this where it's bad, yeah, I suppose maybe you can just put bad on it, but maybe a proper thing to do is to just bag it or indicate that it's out of service or take it out of service altogether instead of just writing some paint on it. But good that they took the time to make sure that they noted for everyone that it doesn't work. So in an emergency, somebody wasn't wasting time trying to use it. All right, hydrant flowing. There's lots of different things to consider when you're doing hydrant flowing. One thing that we always like to do when we can do it is make sure that we can test for water flow out of hydrants. So it's very good practice for us to make sure that we understand what kind of flow we can get from what hydrants. That way we can make sure to update our firefighting folk to let them know what is available at all the different hydrants. And it also helps tell us when we're starting to lose flow over time that we're having issues with the water mains associated, right? Or valving or something else, right? If we can't get a flow that we anticipate to come out of a hydrant that we know we've achieved previously, then there's something going on larger. So specifically what he's got going here is there's actually, it's a little hard to see from this picture because the arm's in the way, but this actually is a Y apparatus. On this side of the Y is actually where you see, no, you can see it right here under his hand. It's a static pressure gauge. So as this hydrant is open, that static pressure gauge is giving a constant read of the pressure that's entering, and then they're allowing themselves off of this side to actually get flow from the hydrant. So with that static pressure gauge and this pitot blade, which gives you a pressure reading right at the orifice of this, if you hold this in line properly, you take these readings and you can calculate what the flow is off of this meter. I will say that there's some calculations involved there, but we're not going to go through the calculations in this course. Pressure gauges are extremely important in our, oh, no, sorry, I'm getting ahead of myself. This is actually a manufactured pitot gauge that can just be fixed onto the end of a nozzle on a hydrant. It's kind of nice because it tells you exactly what the gallons per minute are. Wow, sorry, I don't know what happened there. It tells you exactly what the gallons per minute are here as water is flowing through it. The only setback with these is that you've got to basically make sure that the hydrant is flowing quite heavily so that it is right down the center flow path and hitting that. Whereas with a blade style, you can find the thickest area of flow and you can yourself put that into the flow path to make sure that you're getting it. So this kind of, the only limitation is you've really got to flow a hydrant pretty hard to get good readings on this. I mean, as you can see, the first marker here is 380 gallons per minute. So you're really blowing some water by the time you're getting this gauge to read. Hydrant flushing. Hydrant flushing is, as we're talking about, an important way to make sure that you're removing sediment and cleaning water main on a routine basis so that we can keep all the sediment that builds up along the bottom of the pipe out of the system and try to keep the amount of scale formation on the inside of the pipe to somewhat of a minimum. We don't want it to get so large that it starts causing us flow issues. So you flow these hydrants to do that. This specific hydrant, as you can see, is causing an issue in the roadway. So you have to be paying attention to where the water that you're dispersing out of a hydrant is going and properly closing traffic or avoiding traffic issues such as this, making sure that you've got the right controls in place. The elevation and location of hydrants may change what you have to do to properly flow or flush a hydrant. As you can see, this one here's elevation in relationship to the curb back is not very good. And you can see they've actually tested that, right? If you take this pump nozzle off and you open this up and just blow it straight out, it's going to hit this curb back, erode this curb back, and you might lose your curb altogether. So this is not an ideal situation for a full flow out the pumper nozzle to atmosphere because it'll erode this groundway and cause all kinds of problems. But there's things you can use to try to help this situation, like diffusers. I think this is actually kind of a homemade diffuser that somebody made. It looks like it's a cone that they've put a threading on and then attached a tarp to it. But there's more professional ones out there, kind of like this one here. So this is a diffuser that you can purchase right off the shelf that'll attach to a hydrant. These diffusers help do two things. They help diffuse the water, but then also dissipate the energy that's coming off. So you can still flow these at quite high volume rates. You can actually sometimes get a gauge on here that's calibrated that will tell you flow. And if it doesn't tell you flow, it can tell you pressure. So if you have another static pressure gauge up or downstream or both, you can look at the pressure drop in a relationship to the pressure that's coming out of this. And you can do some calculations to figure out flow pretty easily. But this helps so that you're not eroding ground, you're not tearing up curb back. You can blow it out this way without literally tearing up all the infrastructure that's around it. Here's another device that can be used. As you can see, they've got a truck mounted energy diffuser or dissipator here. This isn't really a diffuser. So a diffuser kind of blows the water into more of a mist style condition so that it's a little less aggressive. This is more of just an energy dissipator. So as the water is flowing off the pumper nozzle and hitting this, it starts to diffuse or displace that energy into multiple paths so that it's not quite as hard. This is a really good example of a setup that they've built themselves. I think this was the city of Portland, if I'm recalling right. And they would go down to their dead end locations. They had a few or several, I think several actual dead end locations in their system, and they would go to those last hydrants in those dead ends and do this flowing, and always saw a continual improvement to customer water quality in those areas every time they would do this. So they just did it routinely. Here's a little bit of some calculations. We're not going to dive in hard. I think you've already done a little bit of an understanding of this with maybe the second session of this series in terms of Q equals VA and understanding how velocity and area work in terms of flow. But the main thing that I want you to understand here is that when you're going to go out and you're going to do hydrant flushing, you need to have a plan. It's not as simple as just go out, open up hydrants, let them run for a while, and then close them down. Because the issue that you can have there is if you open these hydrants up and you do it in such a way that you are flowing your hydrant too fast, yes, I said that, too fast, you can get your velocities of your water high enough to where you're starting to actually cause damage to the distribution system. So it's good to do some quick calculations and have some understanding of how far or how fast or how hard to run hydrants in your system such that you're not causing an increase in the water velocity within the system that can cause detrimental damage. So typically we like to see flow rates hit at least 3 feet per second. And that's not flow rates, that's velocity, sorry. We typically like to see velocities of water in water main when you're doing flushing activities for the sake of cleaning to hit, around 3 feet per second or greater. But we want to keep that probably between that 3 to 6 feet per second. Anything kind of getting over 6 feet per second, you got to start asking yourself if you're doing the right thing. And if we do some quick calculations and we help people understand how this becomes important, okay? So if I've got 1,500 gallons per minute of flow through one hydrant, but fed by 3 pieces of 6-inch pipe, meaning that I'm unilaterally, or I'm sorry, not unilaterally, unidirectionally flowing 3 separate 6-inch pipes towards that hydrant. Each one of those 6-inch locations or those 6-inch pipes will witness about a 5.7 foot per second flow within them. But if I close that all down and I'm running one 6-inch line to that hydrant at that same rate of 1,500 gallons per minute, that's a velocity of 17 feet per second. That's well above any acceptable standard. So you just have to kind of have an understanding of when you're flowing these hydrants, how fast you're moving that water and what you're trying to do in that relationship. If you're just trying to see what is the absolute highest volume of water I can get out of this pipe in an emergency condition like firefighting, then you may have to find out if you can get to that 1,500 gallon per minute within that area. Usually if you're doing that without unidirectionally flushing, that's probably not such a big deal to the distribution system. The only part of the distribution system that's seeing that 17 feet per second is that 6-inch run that's heading to that hydrant, which is not a very large run typically and is fairly easy to replace if necessary, if it breaks down for some reason. So we don't worry too much about hydrant leads. We're more worried about the mains that are out in the street. That's the critical infrastructure we're trying to protect, it not getting over 17 feet per second. So usually if you got the whole system open and you've got several pathways flowing towards it, you can stay under that 17 feet per second and still hit, your 1,000, 1,500 gallon per minute flow rate you're looking for. But in the conditions where you're doing unidirectional flushing, you're not going to want to hit these kind of feet per second. All right, so this is just a quick little exercise to help us go through how we would do some unilateral, or not unilateral, I keep saying that, I'm sorry. I've been dealing with a lot of consent orders in unilateral orders lately, so I've got that stuck in the brain. No, unidirectional flushing paths is what we're trying to do here. So this is our little, made up system where we've got a few hydrants. We've got a little bit of a grid going on here. Our water flow is entering from this location here. And what our idea to do here is to shut down valves in such a way that we can get a unidirectional flow through the system to flush the water mains, okay? Now, there's many different ways that this can be done, but the idea is that you should take a minute to have a pregame to think about how am I going to get there? What valves am I going to close? What hydrant am I going to utilize to get a unidirectional flush going that is the least amount of effort, right? So you want to get the longest run for the least amount of valves to the farthest hydrant you can for each one. So for this scenario, we've picked to close off valves 12, 6, 11, 5, and 4. And then once we've closed them off, you can see our flow path now is in this direction, right? Because up against the closed valves, we're not going to flow. We've opened this hydrant down here, hydrant 2. So this is the path of unidirectional flow that we would achieve all the way to that hydrant, okay? So that helps us clean all of that piping all in one fell swoop. Now, to do this, we also have to understand how long is this run, right? And how fast are we flowing so that we know how long we need to do this flushing to get material that is maybe associated with this main out that hydrant. Okay, so there's a little bit of math, a little bit of thinking to do here, but it's not the end of the day. It's fairly straightforward. Once you know the calculations, you know what you're doing, you can get there pretty easy. So now let's say we flushed for the appropriate amount of time in this direction. Now we want to change our valving around so that we can flush another segment. So in this picture, we've flipped around. Now we're closing valve 2, 6, 10, 8, and 5, and the other corresponding valves that we had closed, we have now opened. So now our flow path looks a little different. Now our flow path is in this direction. We're going to come across here and up and out this hydrant because another long cleaning swoop, right? Again, we're going to flow that until we get all the material that's in this chunk here or in this chunk here out of H2, right? So once we have hit that length of time, we're now going to switch our valves over again. And as you can see with that change in valving, this is now our current run and the last set of pipe that we need to flow through to get a good clean out of this whole little network, right? So we've closed off our valves here to isolate just this run. We've opened the run and we've begun to flow. We are now flowing through this situation here so that we can get this whole grid cleaned out with a unidirectional flow. I hope that makes sense. It's, I think, fairly easy from your handouts to see the progression. If I remember right, while this looks like automation, or animation, it's not animation. It's just literally flipping through the slides. So you should see the progression on your handouts. Hydrant attachments, there's all kinds of different hydrant attachments that are out there. This specific one that we're looking at here is a pressure relief valve, or also known as a blow-off valve. So these blow-off valves are typically used when a community has to take a tank out of service. So they might be using a VFD pump or an on-off, quick on-off pump that is working directly from the plant or from other things without storage as a cushion to that immediate or instantaneous energy surge. So to keep from breaking water main and having other problems, we put blow-offs in the system to dissipate extra energy when it comes through, right? So this is a fairly interesting setup. I'll just tell you that while I can see what they're trying to do is, kind of control the flow of the water into a path they want. As you can see, we're getting the standing water conditions down here. So this actually could become a cross connection because this is not a ASCE certified backflow preventer. This is a blow off valve, right? We have direct connection and can actually get submergence of the end of this outlet. So this is not an ideal setup for a blow-off valve in a distribution system. This is an ideal setup for a blow-off valve in a distribution system where you've got an air gap between where the water is flowing to and any standing water. There's no way you can get a backflow event to occur in this scenario. In this previous scenario, if the water main out in front was to break and start to cause a suction event, this could actually try to suck down. And if this didn't seal properly, you would get some breakthrough into the distribution system. The likelihood is probably pretty small. I will admit that right now. The likelihood is not high that this is going to fail in such a way that you're going to get a backflow event to occur. Now, with that being said, is it impossible? No. So when it's not impossible, that means it's possible. So you need to make sure you've properly protected against it. This is how you do that. Other attachments, a lot of times folks want to try to use hydrants as temporary water for construction or other activities. So you can easily find connection to this. In this specific instance, what was happening here was the municipality was trying to flow a hydrant into this bucket to find out if they were having discolored water come in. So that's why a very nice white bucket with the hose dribbled into it to just flow it and see what's going on. Intentions were very good here as to why they were doing this, but again, this could be a potential cross connection, right? So as water builds up in here, this is just an open and closed valve. There's no real backflow prevention associated with this. So if for some reason a backflow or a back surge event happened on the water main side, it could create suction and would pull this right back into the water system. This hose, is beautifully green as it is I'm sure not an actual potable water hose. Pressure gauges are extremely important throughout our distribution systems. They do all kinds of stuff for us to tell us what's happening inside the distribution system or within pumping stations or other things. So understanding pressure and understanding how to read pressure gauges is a very critical part of proper operation of a distribution system. This here is a setup to actually have backflow prevention occur. This is very good, right? You've got a dual check here with a pressure relief. So this is actually a PRV. This is a great scenario for stopping a backflow event from happening and contaminating the water supply. The only note I would have here is that this is getting to be a pretty long lever out to this point here, or even this point here. So that's putting a lot of strain on that nozzle. And so you might want to actually have some kind of little makeshift stand or a 2x4 or something here to just take some of this weight off. But this is a good example of how you can isolate a use of temporary water in such a way that it doesn't cause an issue for the hydrant or water system. This I actually think is, I want to say this might be Brighton, Michigan. I think that this is directly related to the well house that's over here. This is how they can blow off wells and do other things in that location. So another issue here is when you have water crossings or under I don't want to call it a crossing. I guess you're crossing it, but you're really going under, right? So let's say you've directionally drilled under a lake or a river or a pond or some sort of body of water. If you don't have some proper gauging before and after or other between those points of low end, you could get a break or a leak that occurs under that water body and you would never know it. And the reason you would never know it is because all the water that's daylighting looks as though it's just the water source that was there, especially if it's a river flowing, you would never see the excess water. It would just go. A pond, maybe you would slowly over time see some elevation in the water occur, but the likelihood that you'd notice it in any kind of timely fashion is really, really low. So just be aware that if you have, we'll call them crossings around water bodies, that you really need to make sure that either from time to time you check the pressure associated with the hydrant before or after, which, by the way, a hydrant is almost always required in these scenarios. The other potential you can have is a meter requirement before and either before or after a crossing, so that you can see that water is flowing through this location as you would anticipate, and that there's not some change in condition over time here. All right, something else that's very important to understand about components that can connect to hydrants is that not all hydrant threading is the same. So there are several different thread types here. You've got NPSH, you've got NH, and you've got NPT. So NPT is your national pipe thread. This is what you're typically going to find at the hardware stores, right? You're going to find black pipe or other iron fittings or steel fittings that have this type of threading. This threading is not compatible with all hydrants. NPT is compatible with NPSH female threading. It is not compatible on the NPSH male threading. So you can't go get a female NPT coupling and hook to an NPSH male. It's not going to work. Same thing with the NH females and NH males. Your NPT threadings are not going to work in those scenarios. They will look like they're going to work. They will act like they're going to work, but what you will never achieve is a seal. They will always leak. So just know that there's different thread types that are associated with hydrant or fire hydrants and hosing that are out there. So make sure you are adapting appropriately. And it's also important to note that when you're ordering hydrants, there's these different conditions, so that make sure to always be consistent. Valve turning is a very important exercise that needs to occur regularly within our distribution system. Valves are necessary to isolate portions of the system when we have to work on them or do other maintenance to those portions. Valves help minimize the impact of the public if we have an emergency or some other thing that's occurring. And then they'll have limited ability, if not exercise. So meaning that if you don't exercise a valve over time, you have many things happen. You can have rusting occur to the valve stem or body that makes it such that you can't get the valve to turn appropriately. You can have internal corrosion issues or scaling buildup issues that make it so that you can't get a proper seal on the valve because there's too much gunk essentially in the way. So when you're trying to close the valve down, it doesn't seem to want to. There's valves in the system that are more and less prone to these issues, like resilient wedge valves are typically less prone to issues of closure from scaling and other things like that. Butterfly valves, on the other hand, are ones that are very prone to having issues with scale buildup and not being able to get a proper seal on the valve. So valve turning or exercising, we can use those terms kind of interchanging or interchangeably. You need to, again, make a plan. It's not very smart to just go out into the distribution system and start shutting valves and opening valves without some sort of plan or understanding of what you're doing. And you can go out and start turning a valve and think you're turning it in an appropriate way, and you're actually opening it more instead of closing it, or you're busting valve stems because you're torquing too hard on top trying to get something to move in a direction it's not designed to move in, right? So it's important to know what the valve is that you're going to exercise, what its typical operation is on that operational nut. If it's left hand open, right hand open, left hand closed, right hand closed, those are important things to know. Making sure that you've got the proper connection to the operating nut on top of the valve is important. And then also know what you're shutting down. Make sure you're not just exercising a valve that's going to shut an entire leg off without giving anybody a heads up, right? So you've got to make sure that you're not isolating portions of the system while you're doing exercising. And if you are isolating portions of the system while doing exercising, that maybe you're doing those in the middle of the night when water usage is low, or you're advising the customers that are on that leg, hey, you might have a moment here where you're not going to have as much water pressure as I do this. So if you could just avoid using the water while I exercise this valve for the next half hour or hour, that would be appreciated, kind of thing. So making a plan is very important. Coordinate with your flushing. As you're opening and closing or exercising a valve, you are going to release some scale material from the inside of that valve, or you're very likely to release some. So doing it in coordination with flushing is also helpful. The other piece of that is, as you saw in that previous exercise, when you're trying to do unidirectional flushing and you're opening and closing valves to get that unidirectional flushing, that's a good time to know you're properly exercising your valves and getting things closed and opened appropriately. So you can do these in tandem. They don't have to be two separate maintenance activities. Always record your efforts. Record things like inoperable stems. Record when something turns in a different direction than what you anticipated. Record any inability to completely seal. Record all the things that you can figure out about those valves as you're doing the operations. All right, so this is a little valve operation exercise here. It works very similar to the flushing exercise that we saw. So as you can see, we can start to show that if we have an emergency occur, what the issue is if we don't have proper valves exercising and we have to go out into the system and we need to isolate a leak. So here we got our emergency occurred. We've got a broken water main down this leg of water main here. And what we want to do is isolate that. So we go out, we close the first valve, we're successful. We go to close the second valve, we're unsuccessful. The valve won't move, won't close. We can't get a seal. We're having continued issues. We can't isolate. So then we move to other valves. We're able to get success out of these two valves. That's excellent. They closed up nicely for us. We tried this third valve, not so good. Didn't get closure, had an issue. Move out to the next two valves. Finally, we were able to get isolation. But now the issue is, had we done or had been implementing a valve exercising program and identified that these were two bad valves in the first place and dealt with them in an appropriate amount of time, we would have been able to isolate just this section of the community. So just this section of the community would have had an impact. But now instead, we've got this entire leg of the community that actually has been now affected by this section. Even though we had the appropriate valving to do something smaller, it wasn't operable. So it was as if we did not have the proper valving. The other piece of this is, here you are in a situation where you're trying to handle this in a short amount of time so you can minimize the impact from this water leak. If you were able to just close two valves, that's a heck of a lot less time than if you have to close 1, 2, 3, 4, 5, 6, 7 valves effectually to get there, right? Especially because these two valves, I guarantee you're dinking around with them, trying to figure out, why won't it close? What's going on? I can't seem to get this thing to seal up, and before you're moving on to other ones, right? So this is going to cost you a lot of extra time that you wouldn't have had to do if you'd had a proper valve turning program and I had identified that these were an issue. I mean, if you went into the field and this was the case, and you knew from your valve exercising program that these two valves are bad and could just immediately go to these other ones, that also is a time saver. So just because you haven't had a chance to get to a known broken valve, it still puts you in a better condition knowing they're broken than having to get out there to find out they're broken. All right, so making rounds. We talked about this earlier, making sure you got your eyes and ears open as you're heading around the distribution system and looking at everything that's going on. Pay attention to water that's in places that you don't anticipate water to be in. That might be daylighting occurring from a leaking main. Visit facilities and pump stations. Make sure that things are all working and look like they should be, and that there isn't something else happening. I can't tell you the number of times that operators, by doing rounds, have identified problems before they've become catastrophic. For example, I think, I can't remember the system now, a system operator and I visited a pump station, and as soon as we walked in the door, the operator and I looked at each other and we knew instantly that one of the pumps was cavitating and about to explode. You could hear the pinging and the eruption of the inside of the propeller on that motor just going bananas. Had we not visited at that moment or in that day, we would not have recognized that motor probably would have failed, and then they would have had some issues in distribution that they would have had to been in kind of an emergency condition. Instead, because we found out by doing around and we did that inspection, we figured out that was going on, we were able to reroute another pumping station, turn that pumping station off, and get it dealt with without having any disruption to the distribution system at all. So making rounds is extremely important. The other big thing to do is check your residuals out there when you're doing rounds. Make sure that you're getting residuals that you anticipate, that things look as they should, and that you're not having drops or increases in residual that are abnormal. It's always good to be checking our water, make sure we know what's going on. And then we got just a few more slides here, but essentially what we're thinking here is this is the great unknown, right? So you can't see water main, you don't know what's going on necessarily, so we have to use all of these other things we've talked about as indicators of operation, ways to get a good idea of what's happening without being able to necessarily put our eyes on it. This is why that second session of water concepts is so important for distribution operations to be able to understand what is going on. I have a drop in pressure, why? I have an increase in pressure, why? I have a flow condition I can't control. Where's the water coming from? Understanding all of these things is what helps you deal with these situations. Chlorination is a big piece of distribution operation. If we don't have proper disinfection occurring in the distribution system, it can cause us some real heartache. So the distribution or chlorination has been around since the 18th century, which is when it was discovered. 1810, it identified and named itself as being chlorine and chlorination, implemented into the war times. That was where they first started trying to use chlorine, or chlorination was to actually use it as a weapon, not necessarily as a tool of protecting public health, but actually harming public health. It then was able to be understood that, hey, we could implement this into water in small volumes, small concentrations, and it's a very positive effect for our systems. It helps neutralize those unwanted bacteria and other microbes and such that get in the water. And it's also used quite heavily in manufacturing of other things. Disinfecting power is all about the disinfectant's ability to kill or inactivate viruses and bacterium and other microbes. It's part of our multiple barrier of defense. So we keep a pressure in the system. We do good treatment practice at our plant. We have good aseptic techniques, but our last line of defense essentially is disinfection. That's how we make sure that the last piece is in place to keep these parasites and bacterium and other microbes at bay. Very useful tool. Chlorination has a break point. So a lot of people think when they're getting complaints around taste and odor issues with chlorine that, man, they need to back that chlorine off. Well, a lot of times this isn't necessarily true. It's just the opposite that needs to occur. And the reason for that is because as you have organics in the water and you're adding chlorine, you're starting to get an increase in your residual concentration, right? So you're adding chlorine, your residual concentration is coming up, and then all of a sudden you hit this point where it's like, no matter how much more chlorine I add, I'm not gaining in residual. I actually am starting to lose residual, starting to drop off on me. This right here is because you're trying to hit break point. You're in the downward slope. So you're burning up any ammonia that's in the water, some other issues that are in the water that chew up chlorine. You're burning through those things. This area right here is why you get complaints around a pool type odor or smell in your drinking water associated with chlorine. You keep feeding chlorine, you'll actually get to the bottom of this. And then when you start coming out the backside, this is when you're going to get odorless chlorination in your system. You've burned through all of those things that create that chlorine odor in the water, and you're actually starting to get water that's free of those spent up combined chlorine issues. You're starting to get to the free chlorine piece, and that free chlorine then starts to build in residual concentration. And you should be able to have somewhere up to about 4 parts per million of chlorination into a system before it's readily detectable by the majority of the population by scent or taste. Or not 4 parts per million. I've said that wrong. It's 2 parts per million. It's up to about 2 parts per million, I think is what it is, where you can get it up there into a point where the population doesn't really smell and taste that chlorination at all. They can't really detect it. But that also comes down to, where you're at on this breakpoint curve. If you get beyond this breakpoint curve and you're in that area up in here, this is when you're going to get very good disinfection, and on top of it, very low odor complaints. Chlorine levels, max and min, 4 parts per million is the highest you want to go in your distribution system. There's actually an MCL that's based on a running annual average for chlorination in a distribution system. So you cannot go continuously above 4 parts per million of chlorination in a distribution system, or you have an MCL violation. Our target levels have typically been between 0.5 and 2 throughout all of distribution for our treated water. I've got that backwards, sorry. Treated water leaving the plant, we're trying to hit this level, I guess is what they're stating here. I don't know that I agree with this totally. I would say if you have between a 0.5 and 2 in distribution, you're doing a good job, is essentially where we're at. Your free and total, you want to make sure that they're preferred in the free range. Free is really where the rubber meets the road. Free chlorine is where you still have a really solid active oxidant available in the distribution system. Chlorine over time, you get off gassing that occurs. So if you get water that's had a long residual time, it becomes an issue in losing those residuals because it can off gas. So think storage tanks. If you've got standing storage tanks with large surface area, you're going to lose chlorine residual in those tanks. Source water and chemical reactions, just chemical reactions in general. If you've got iron in your source water, it's going to chew up your chlorine residual. If you get iron from cast iron mains and pipes that are coming into the water, it's going to chew up your chlorine residual. There's lots of things that will react with chlorine. Chlorine is very reactive, and it makes it very hard to maintain a residual in the system. Cleaning and flushing your water mains is one very solid way to regain your ability to retain a chlorine residual. This is a little example of like where to pick to check for chlorine residuals. It's pretty obvious. You want to get to the extents of your system. So I'm not going to really run through these exercises. Just realize like your worst case scenario is typically where you're trying to meet chlorination targets and objectives. Trying to get that 0.5 to 0.2 to 0.5 in your worst areas will mean that the rest of the system is real healthy. Last little piece, we already talked about this a little bit. If you've got a leak that's occurring and you're starting to lose pressure, if you drop below that emergency pressure condition, you need to be starting to think about issuing a boil water advisory. Make sure that you are always safely excavating to get down, you're properly swabbing your pipes if you have lost pressure, and that you're doing the things that you need to do to make sure that you are keeping as clean of a situation as possible. And then almost always when you have a leak, it's a good idea to take some back-T tests. Controlled depressurization is key. If you can depressurize controlled wise, that'll help keep the site itself of the break as clean as possible, keeping material and debris out of the pipe. Again, you're going to probably have to do a boil water advisory. You're going to have to do some back-T testing. But in this scenario, you're doing the best kind of cleanup that you can of the exterior of the pipe. So some depressurization caveats. Flush a lot after you've got the situation cleaned up and fixed. Make sure that before that you've properly swabbed with at least a 1% chlorine solution to the existing. If it gets even larger than that, you may have to increase that chlorination or chlorination time all the way down to how you would typically put new main into service with doing a prolonged hold of high chlorination. There's all kinds of things to do here, but if it's not controlled, that's what we're saying. Full chlorination is going to be key. So this is just communicating boil water advisories. If you have a loss of pressure, and remember, loss of pressure is below emergency pressure, not total loss of pressure, or even what we consider to be partial losses, you have to start thinking about boil water advisories and communicating those. It is very imperative that you contact the department and talk to the department whenever you think you're going to be issuing a boil water advisory. Unless you absolutely know you've lost pressure, just get on that boil water advisory right away and then start contacting